What you see in front of you right now is a table. It's gotten from Institutional Effectiveness of PCC, and it gives you age distribution. And I want to talk about bias and sampling. So out of these categories, let's say I focus on the 2024 group. So I'm going to divide my population into those that are in that age group and those that are not. And there you have it. I've divided my population into those that are in the age group 2024 and those that are not. I'm going to rewrite this one more time in the context that you've been seeing this information. And here I have it. I'm counting successes being in this age group 2024, and I got a 30.7% chance of success on any given observation, and 0 means it did not count success, and I have 0.693. And if I calculate the mean of this distribution, and the mean is just going to be, again, outcome times its probability, and then the sum of these two, which of course is 0.307, and this is what we've been calling P, the probability of success, and it's the mean of this distribution right here. The goal of statistics is to estimate these means. So in the information you have right now, you're being given these values, but shortly we will not be given this value, and you're supposed to be able to estimate it. We can't get this number exactly, but you can estimate approximately what that value, and that is only through sampling. So if I want to estimate P, I'm going to use P hat to estimate it. And in order to estimate, I need to sample. And let's just pick a number. I'm going to say I'm going to choose n equals 100. In other words, I'm going to sample 100 times from this population consisting of students, and I'm going to calculate the proportion of those that fit into this category 20 to 24. Now I'm going to simulate sampling 100 times from this distribution, and I'll use Excel's rand between. So I'm going to write if rand between, I could just spell here. So I'm going to randomly select an integer between 1 and 1000, but if I want that number to be less than 308. If a number is less than 308, give me a success. Otherwise, give me a failure. And since rand between is just doing it randomly, and I'm choosing from 1,000 numbers, 30.7% of the time, I should get a number less than or equal to 307, and that will give me success. Otherwise, it's a failure. So on my first attempt, I get a failure, and now I'm going to do this 100 more times. Hang on. Okay, I got my enumeration here. Let me get this one more number here. There we go. And you can see, because I'm using rand between, this will continue to change as I go through the whole thing, but I need to get 100, so I'm going to just get 100 numbers here. Great. I got my 100 numbers. I'm going to come back and just average all these numbers out. I'm going to just make sure I got them all. Okay, and that should be it. So notice my simulation produced a 0.3. This is p hat. So that number right there you see is p hat, and of course these numbers keep changing. Every time I hit enter, it will change. So in order for me to stop from changing it, I'm going to grab all these. I'm going to grab all these numbers, all of them, copy, and do a quick paste special here. 1, 2, 3. There we go. Now everything's fixed. Great. Yeah, this one keeps changing. It will keep on changing every time, but now I've fixed these numbers by doing that space special. Fantastic. So my estimate was 0.35 out of 100 numbers. That's p hat. Great. Rand between supposedly is an unbiased, has an unbiased sampling procedure, so this number is the result of an unbiased process. So the question becomes, what is bias? Bias simply means that your procedure is such that this number, this value right here, is not what is being portrayed. So maybe I sample in such a way that in this case, um, I'm not going to get this number, uh, the quoted number of times. So in order for this to be biased, here's what all that would happen. I would have a sampling method such that, let's say that for whatever reason, even though I'm after this particular group, I sample in such a way, maybe I sample too many evening courses or something that will skew the results. And let's say now that I get this, I'm going to exaggerate it here, 0.22 and 0.78, right? So this is reality right here. This table is reality, but my sampling process is such that um, I'm really producing somebody in this age group 22% of the time instead of the actual 30% of the time. So of course, in this case, no matter what I do, my sampling procedure will produce a different p-value, or sorry, p-hat value. So if I do the same calculation, success times relative frequency, I'll get a population proportion of p.22. So all of a sudden you have a bias. With a bias, all of a sudden the means are not equal. And that's all that bias means, is that somehow your sampling process is such that you're sampling in a manner that it doesn't meet this. Now, does that mean that your sampling process must be such that there is absolutely zero bias? No, no, because the way we're going to estimate these parameters has a bit of leeway. So there should be no bias, but that would be asking too much. Instead, what we're asking is that the bias, whatever it is so small that will make the estimation nearly have no difference, as if there was zero bias. So I'm going to do one more thing here. I'm going to create a binomial situation. Since I'm sampling in such a way that I meet the binomial criteria. So my probability of success is 0.307. I'm going to reduce the sample size here just so we don't go off screen, and I'm just going to go n equals 10. So that's my sample size. And they wouldn't matter. I could do it for a sample size of 3. Sample size will not make any difference. The only thing that sample size does is alters the variation of my p-hat value, or whatever is my statistic value. So the bigger the sample size, the variation of my statistic will be reduced. So if I only do a sample size of 3, of course my variation will be larger than if I did a sample size of 10. But this doesn't alter the mean. The means are identical. So I'm going to create another table here. What I'm doing is I'm counting my successes. I'm going to do it 10 times. This is a binomial, so I'm going to write binom dist. Probability of success is 0. No, sorry. This is the success I'm looking for. The number of trials is 10. Probability of success is 0.307 and false, so that means I'll get exactly that value right there. And a sample is 10, the chance of getting no successes, mean none of the students are in that age group, is about 2.5% chance of that. Notice the chance of only one student is 11%. Now I'm going to just do it for the rest of these. There's 10, I hope. Yep, there it is, 10. And here we have, so either 0 successes all the way to 10, and that's the probability of getting these numbers. So these numbers right here are statistics, possible statistics values. The number of successes is just a statistic. Here, all I'm doing is taking my success and dividing it by 10, so that is my p hat. And again, this probability is the same thing as this probability applies to binomial, and it also applies to p hat. Great. Now, what is the mean of this distribution? Well, again, I'm assuming when I did this calculation using this formula, this binom dist formula, it's completely independent. It's no bias in the process. So this is the best of everything. So that means that the mean of this p hat, I'm going to use p hat. The purpose of p hat is to estimate p. So for example, if I got 2 successes out of the 10, which is a 22% chance of that happening, I would estimate that the true proportion of students in the age group 20 to 24 is 20% as a point estimate. If I got 3 students out of the 10, then I would estimate that it is 30%. And of course, you might be saying, gosh, that's a huge jump, 20, that's a 10%. Well, yes, that's why we increase the sample size to give them more choices, and then we get a better estimate. So with 10, you're not going to get a great estimate. But the question I have for you is, what is the mean of this distribution, which is a sampling distribution of p hat? What is the mean? Well, because my process is unbiased, all of a sudden, that value should be 0.307. Let's try it. So what is the mean of this distribution? Well, the mean consists of taking this value times its probability and doing it the same for every single one of these, and then summing up all these numbers, and because again it's a discrete table, and there you go. That is P, but this is not P, this is E of P hat, which happens to be equal to in value to P, the one over here. So this is kind of a sample of 1, either 0 successes or 1 success, while this is a sample of 10, and you get P. But you'll notice if I sample 3 times, so here I've created on the table, I'm only going to sample 3 times this time. I need to change this. So this is going to be divided by 3. Okay, and so this number is going to be again divided by 3. Great. And I'm only going to do it 3 times. I need to change the probability of success. Nope. Sample size is only 3. Okay. So I'm altering everything. Here we go. So there you go. Either have 0 successes all the way to 3. That's all I can have. So obviously this is a different sample size, but sample size has nothing to do with the mean of the distribution of my statistic equaling to the mean of the population I'm sampling from. So this is the population I'm sampling from, where so you have a chance to imagine it's a die or a coin, where one side is the thing you want to happen, that happens 30% of the time. The thing you don't want to happen happens almost 70% of the time. That's the way you want to look at it. That's all that's happening here. But the number of times that you flip, I guess, this coin has nothing to do with the distribution mean, the sampling distribution mean. So again, if I ask myself, what is the mean of this? All I have to do is take outcome times probability sum. And again, there you have it. So E of P hat now, but again, different sample size, continues to be 0.307. Sample size has nothing to do, sample size has nothing to do with the mean of this distribution being equal to the mean of the distribution you're sampling from. Okay, so for binomial, think of it as the distribution you're sampling from like a coin flip. But a coin, instead of being 50-50, it could be whatever success is, the probability of success is. So what the heck is bias? Simple. Simple. Bias just means that somehow, like we already mentioned, this probability of success, it's you sample in such a way that all of a sudden it doesn't match the population real, the probability of success for the population. Somehow you're sampling in an incorrect manner or a biased manner, really. That's what we're saying. It's biased. So if, for example, let me just go back over here, we go back and say, no, it's we're sampling in such a way that it's really 0.22, then of course, when I come over here and change everything, you'll notice, boom, there you go. Now it equals my biased probability of success, 0.22. What if it's, I mean, it's biased, but it's, my gosh, it's not that biased. Well, gosh, if it's not that biased, let's say somehow that is 0.29. Well, guess what? If it's 0.29, that's my bias. There you go. That comes out to 0.29. So the issue is, as we're always going to have some bias, but we don't want them to be this. If it's close, then it's not so bad because we can still use that as a pretty good estimator of what the real thing is. It's when it goes to the to an extreme that then it doesn't really matter how much you sample. I could sample 1,000 times with a biased sampling method. It doesn't mean I will get a good result. As a matter of fact, I'll get a worse result because if I sampled 1,000 times, then that would think, oh my gosh, I've sampled 1,000 times. That means I must be really close, and it's taking you somewhere else. So if I change this to 1,000, what would be the mean of p hat under a bias condition? It would be this, whatever the bias is. That's what would show up, and I would think, gosh, I really know what's going on. So if it's really not that much of a bias, 29%, 30.7%, depending on the application, who cares? But if it's really, really, really bad, that situation is bad, I change it now here, and let's say that this is like 0.22 and I sampled 1,000 times. Of course, I'm not going to do this 1,000 times, but all that would mean is that this number would change to 0.22, and I'm thinking, gosh, I sampled 1,000 times. It must be really close to 0.22, and that's what my estimate would show, and I think I'm happy. And in the end, it turns out that no, that number is actually completely worthless because of my bias sampling procedure. So the mean of this distribution is equal to the mean of the population I'm sampling from only if and only if my sampling procedure is unbiased. If you have a biased sampling procedure, no amount of sample size will rescue you. So E of, I guess, n for this, n equals 1, or I don't even know how to, there's no notation for this, is equal E of p hat if and only if my sampling procedure is unbiased.